Let's elucidate quantum cryptanalysis. In this video, we're going to see how integer factorization and the discrete logarithm problem can be thought of as hidden subgroup problems. In a hidden subgroup problem, the goal is to find a generating set for the hidden subgroup H. H is a subgroup of the finitely generated group G. Consider the function f, which maps from the finitely generated group G to a finite set X. Let's impose a very important condition on this function f. For any two elements, G1 and G2, in the finitely generated group G, f of G1 is equal to f of G2 if and only if G1H is equal to G2H. What is this condition telling us? The function is constant on the cosets of the hidden subgroup and distinct on each coset. So this is a very important property for this function. So we can think of this function as hiding the hidden subgroup H. And we're going to see that this format can be used to describe the discrete logarithm problem and the order finding problem. Order finding can be connected to integer factorization. So we can treat integer factorization and the discrete logarithm problem as hidden subgroup problems. So we're going to see how we can re-express these problems in this format. We're going to define a function from a group to a finite set, and we're going to see how that function is constant on all of the cosets of the hidden subgroup and distinct on each coset. Let's begin by defining integer factorization and seeing the link with order finding. So the input for integer factorization is the positive integer n. The goal is to find the prime factorization of this positive integer n. To do that, we're going to choose a value a, and we're going to define a value r. All three of these values are elements of the natural numbers. And we're excluding 0 over here. So this is the same as the positive integers. Now, let's impose some conditions on a. So n is the input. We're trying to find the prime factorization of n. And then we're going to choose a value of a. And that value of a has to be between 1 and n. That's the first condition that we're going to impose. The second condition is that the greatest common divisor of a and n is equal to 1. That means that a and n are co-prime. Now let's define r in terms of a and n. So r is the order of a. And we can denote that with these vertical bars. What does that mean? What does it mean to be the order of a? Let's write down an important definition. A to the power of r is equal to 1 mod n. And something is very special about this value of r here. R is the smallest positive integer such that a to the power of r is equal to 1 mod n. So that's what we mean when we say the order of a mod n. And the goal is to find r. So we begin with the input n. We choose a value of a which satisfies these two conditions. A has to be between 1 and n, and it has to be co-prime with n. And then we need to find the order of a mod n. And the order of a mod n is this r over here. That is the smallest positive integer that satisfies this relationship. And now, if we manage to successfully find the order, we can use that to develop a guess for a factor of n. So this is a very important insight in Shor's factoring algorithm. if 2 divides r and a to the power of r on 2 is not equal to -1, then we can compute a guess. And we have two options for this guess. The greatest common divisor of the quantity a to the r on 2 plus or -1, those are the two options, with n. So if we consider these two quantities with this plus or minus possibility, and we compute the greatest common divisor of this quantity with n, then we're going to have a guess. And that is going to be a guess for a factor of n. But this procedure might fail. So if r is odd, that's going to cause problems. R needs to be even. 2 needs to divide r. That's because we're dividing r by 2 in this expression over here. And we also need this condition to be satisfied. Let's see where this is coming from. So let's write down a very important relationship in Shor's factoring algorithm. A to the power of r on 2 minus 1 times a to the power of r on 2 plus 1. So these are the two options that we're putting over here in the greatest common divisor with n. And this evaluates to a to the power of r minus 1. Why is that the case? Well, here if we take a to the power of r on 2 times a to the power of r on 2, we get a to the power of r. The mixed terms will cancel, and here we'll have -1 times +1, which is responsible for this -1. And from the definition up here, we can see that a to the r is the same as 1 mod n. So this is the same as 0 mod n. And from now on, I'm not going to explicitly write mod n. It's just going to be implied that we're doing modular arithmetic. We're working mod n. So 0 over here, the additive identity, that is a placeholder for any integer multiple of n. And you can see why this condition is necessary. If a to the r on 2 was equal to -1, then over here we would have -1 plus 1, which would give 0. So we would have 0 on the left-hand side over here and 0 over here. And that would cause some problems with this guess. So this is not guaranteed to work for any choice of a. That's why we have to do this repeatedly. So you can think of this as a guess and check algorithm. And the more times you do it, that's going to increase the probability of success. So that is the deep relationship present between integer factorization and order finding. If you can do order finding efficiently, then you can do integer factorization efficiently. So we've taken this integer factorization problem and we've turned it into an order finding problem. Now let's write the order finding problem in the format of a hidden subgroup problem. So first, let's define two integers z and k. These are elements of the integers. The group G that we're going to be dealing with is going to be the integers under addition. So that's the group that we're interested in. The integers under addition. And we're going to define a function f1, which takes in the input z and maps it to a to the power of z. So that is the function that we're defining over here. And it's taking an integer and it's mapping it to a power of a. The powers of a, they form this finite set, x over here. So that is the set that we're mapping to. And let's try and derive a periodic relationship for this function. And that's going to help us see why this property is satisfied for this particular function. So we can take this a to the power of z and multiply it by the multiplicative identity. That's not going to change anything. So we're going to have a to the power of r, and we can do that multiple times. We can do that k times. So if we multiply by 1 k times, that's not going to change anything here. So that comes from this definition over here. And keep in mind that we're working mod n. So all of this is modular arithmetic. And now we can use exponential laws to bring all of these up in the exponent. So we have z plus kr. And then from the definition of the function, we can rewrite this as f1 as a function of the input z plus kr. So this works for any integer value k, and r is very special because r is the period of this periodic function. And R is also the order of A mod n. So we can see that order finding is a type of period finding. So why does this work? Well, it works because A to the power of kr is equal to the same thing as A to the power of 0, which is equal to 1. It's the multiplicative identity. So we can set k equal to 0 over here, and then we get this special case of A to the power of 0. And if we set k equal to 1, then we get this special case over here, A to the power of r. And then if we have integer multiples of r, that's also going to give us the same result. So that is this function over here. And keep in mind, this is mod n. We're doing modular arithmetic. So we've constructed this function, and we've written the order finding problem in the format of a hidden subgroup problem. And now let's have a look at a connection between the order finding problem and the discrete logarithm problem. So we're going to have to define some more integers. We're going to define s and l. And these are integers, and we're going to specify a further restriction. We're going to say these are members of the set of integers mod r. So assuming that we know the order of A, we're going to continue on and define this discrete logarithm problem. And you can see that order finding and discrete logarithms have a very deep connection. So S and L are both members of the integers mod r. Let's impose a restriction on S. S needs to be between 1 and r. So it's a very similar restriction to what we had up here for A. And I'll show you the reason for that. So let's just have a look at some notation. If we write 1, that's the multiplicative identity. 1 times A, that's the same as A to the power of 1. If we multiply by A again, that's the same as A squared. So that's the notation we're using. That's what this exponential notation means. Now, let's say we have an arbitrary power. Let's say we're raising A to the power of S. What does that mean? We have 1, that's the identity. Then we use the operation of multiplication to combine that A over here. So we have 1 times A, and then we can keep doing this. We go times dot 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 times A, and let's say we do that S times. That's going to give us A to the power of S, and we can write that as the value P. Now, the reason I'm choosing S and P is because in cryptography, we're dealing with a secret value and a public value. So the exponent over here is the secret value, and P is the public value. So if you have this base over here and you raise it to the power of that secret, you're going to get the public value P. So it's very similar to the cryptographic application of integer factorization. This value n, that will go in a public key in RSA cryptography. So in the RSA crypto system, this n goes in the public key. And there's an assumption of computational hardness. So we're assuming that it is very difficult to extract the prime factors out of this value n. And usually in RSA cryptography, you choose a semi-prime value for n. So that means that you have two really large prime numbers, they get multiplied together, and that gives you this n. And then we have a computational hardness assumption. We say it's really hard to extract those prime factors. And that's why that is broadcast as a public value. And in the discrete logarithm-based crypto systems, we broadcast this public value over here. And this exponent is the secret. So we have a secret value and a public value. And we can write this value of S in a more familiar form. We could write this as S is equal to the log base A of P. So now if P and A are known, we want to find the logarithm base A of P. But keep in mind that this is all being done mod n. So we're doing modular arithmetic. This is a discrete logarithm problem. So it's a little bit harder than if we were not imposing this modular arithmetic restriction. So now we've defined what the discrete logarithm problem is. Given this public value P and this base A, we want to find S. That's that secret value. So now let's define a function and rewrite the discrete logarithm problem as a hidden subgroup problem. So we're going to consider a pair of inputs, S and H. We have a pair of inputs, S, H. And that's an element of the integers mod R cross the integers mod R. This is the group that we're dealing. So that's this G up here. And this group has the operation of addition mod R. So we're doing addition mod R. That's the group operation over here. Over here we had a bit of less restrictions for the order finding problem. We just had the integers under addition. But now we have a little more of a restriction because we're assuming that we know the order of A. We know the order of A mod n, and that is this value R. So this is the group that we're starting with, and we're going to be adding these pairs of numbers mod R. Now let's define the function. The function f2 takes the pair of inputs z, h, and it maps them to a to the power of z plus sh. So this secret value is in the definition of this function. This is also a periodic function, but the period is a little more different. So the period is not as simple as just adding a integer multiple of r. So this period is a little more complicated. We can write this as a to the power of z minus ls plus s times h plus l. And from this definition, we can write this as f2 with the input z minus ls, comma, h plus l. So that's what we're dealing with over here. We have minus ls and plus l. And that is actually the period. So the period consists of a pair of values. And we've defined this value L over here. L is also sourced from this set of integers mod R. And this is the periodic relationship that we can identify. So we no longer just have a single value as the period, this R. Now we have a pair of values. And those pair of values are defined by this secret value S. Now let's see some interesting relationships with this function. So f2 of z, h can also be written as f2 of z plus h, 0. So this is actually a special case of this relationship. If you choose this integer L to be minus h, then you can cancel this h over here. So you have h minus h, that gives 0. And if you choose this minus L to be plus h, so that's the opposite sign, that's the same as minus h, which gives us a plus h, that gives us this over here. So we're just substituting the choice of L equals minus h. So that means that minus L is equal to plus h. And then we can also see that this is equivalent to f1 as a function of z plus sh. So this input, if we put it into this function over here, we're going to get the same result as if we put this input and into f2, or if we put this input into f2. So there is a deep relationship between f1 and f2, and we're going to use that relationship later when we construct a quantum algorithm for the discrete logarithm problem. But there's a problem. If we don't know what s is, how are we going to evaluate the function? We need to write this in terms of known values, so in terms of p and a. And we can do that. We can break this up as a to the power of z times a to the power of s to the power of h. That's using the same exponential laws that we used up here in this f1 periodic relationship. And then we can identify that a to the power of s, that's the same as p. That's the public value. So this can be written as a to the power of z times p to the power of h. So these are known values, and we can evaluate the function in terms of these known values. And z and h, they're the pair of inputs. So this is a rather unusual function. It's a function that takes in a pair of integers instead of just a single integer. But it's a very important function that's going to help us understand the discrete logarithm problem and how we can construct an efficient quantum algorithm to do discrete logarithms. Now, let's have a look at one very important property. If we have f2 and we take the input minus ls, comma, l, so that's the same, these pair of values, they are the period for this periodic function. If we put these guys inside here, and then we choose the special case where L is equal to 0, that's going to give us f2 of 0, 0. This is the identity element of the group. So 0, 0, that is the identity. And this identity element is going to get mapped to the identity element in the set. So that's going to get mapped to a to the power of 0, which is equal to 1. And a similar relationship is present for f1. f1 as a function of 0 gets mapped to 1. And this is the same as f1 as a function of k r. That's a multiple of r. So this r over here, that is the period for this periodic function. And this pair of values, minus ls, comma l, that's the period for this periodic function. And you can see that they get mapped to a to the power of 0, which is 1, the multiplicative identity. So both of these functions are mapping to the same set. They're mapping to the powers of a, with an important restriction that a to the power of r is equal to 1. And all of these operations are being done mod n. So now let's have a look at what we are actually trying to find. We're trying to find this value r. So it is this value r that we're looking for. We want to find r. That's order finding. And this value of s, that's the discrete logarithm. So we're also trying to find s. Now, if we find s and if we find r, we will have successfully created a generating set for the hidden subgroups. So for the problem of order finding, r gives you enough information to construct all of the multiples of r. And the set consisting of all the multiples of r, that is the hidden subgroup. So that's what we're trying to find. And what about for the discrete logarithm case? Well, for the discrete logarithm problem, you can see that the set consisting of all of these possible pairs, where we have L and S defining that, that can be determined by just the value of S. So L is any of these integers that are in the set of integers mod R. So this can be 0, this can be 1, 2, and we can have many possible values for L. But what you need to generate that set is this value S. So S contains enough information to generate the hidden subgroup for that discrete logarithm problem. So you can see that discrete logarithms and order finding are intrinsically linked. There's a lot of deep relationships between these problems. And order finding is a type of period finding which can be used to help us do integer factorization. There's so many cryptographic applications here. And the reason I'm defining these functions is because they're going to help us construct quantum algorithms for order finding and discrete logarithms. So let's quickly use f1 as the label of a quantum state. So let's consider a quantum state which is labeled by f1 as a function of the input z. And let's assume that it takes beta qubits to describe this quantum state. Now consider a quantum state like this, which is getting acted on by an operator. We're going to use u sub a to denote that operator. This operator has the effect of multiplying this label by a. And that's going to map this state to the quantum state labeled by f1 as a function of z plus 1. And we're going to use this operator in quantum algorithms for order finding and discrete logarithms. So why is this the case? Well, if we're starting with f1 as a function of z, that's the same as a to the power of z. And if we multiply by a, that's the effect of this unitary operator, we have a to the z times a. And that's equivalent to a to the z plus 1. And that's the input that we have for the function here. And we're going to re-express this state in terms of eigenstates of this unitary operator. So this state can be rewritten as a superposition of the eigenstates of this unitary operator. And that's going to allow us to construct a quantum algorithm for order finding and a related quantum algorithm for discrete logarithms. So we're going to do that with the definitions covered in this video.